welcome back. We are looking at this particular function, rational function, and we are going through the guidelines for sketching. We are at the position of looking at intervals of increase or decrease. For here, you need to compute the derivative. All right. So we need to find critical numbers for fx. Why do we need derivatives? Basically to find the critical numbers. A number c in the domain of f is a critical number if the derivative is 0 or derivative is undefined. So let's look for the derivative. Fx equals 2x minus 3 over x plus 5. So to find the derivative, you need quotient rule. Square of the denominator. What happens to the top? Derivative of the top, that's a 2. Denominator as it is, minus numerator as it is, derivative of the bottom. All right, which is equal. So denominator squared, let me distribute this 2. I get 2x plus 10. Now distribute the negative. Oh, by the way, multiplying by 1 doesn't change anything, right? It's the same thing. So why don't I distribute the negative? So that gives me negative 2x plus 3. Don't forget there is a negative here and a negative here. Plus 3. So what happens? This 2x cancels this 2x. I'm left with 10 plus 3 on the top, that is 13. And denominator is x plus 5, quantity squared. Note, this derivative is undefined for x equals negative 5. But unfortunately, this number is not a critical number because it is not in our domain. Remember, our domain, already we were not allowed negative 5. We had to remove it. So it cannot be a critical number. It is not in our domain. All right. A critical number has to be a number in your domain. Okay. So that doesn't give us anything. What other option do we have to have a critical number? Well, maybe the derivative is 0. So let's take the derivative, set it to 0. Well, this is a fraction, so I'll write this as a fraction, 0 over 1. Cross multiply 13 times 1 equals 0 times this. Well, 0 times this is 0. 13 equals 0. This is impossible. So what went wrong? Well, the only conclusion is this cannot happen. In other words, f prime x cannot be 0. That is, there are no critical numbers. But because our domain is broken, you see, we had to remove a number. We still have 2 intervals. So even though we don't have any critical numbers, we have to check for increase, decrease in these 2 pieces. So how do we check for increasing, decreasing? List out your intervals. I have 2 intervals, negative infinity to negative 5 and negative 5 to positive infinity. Choose a test point. I chose negative 6 in the first interval and 0 in the second interval. Plug this in the derivative. So negative 6 when I plug in, I get this. Denominator squared is positive, 13 is positive, so overall I have positive. That means over here my function is increasing. So let me write that down. My function is increasing in this interval. All right. What about here? Let's take a test number which is 0. Plug it in. 0 plus 5 squared, positive. Numerator is positive. Here also my function is simply increasing. Okay. So my function is actually increasing throughout on its domain. That is, this point is not in its domain. But whatever is its domain, it's increasing. It's not decreasing anywhere. All right. Now, local max and local min. That's the next item to discuss. Okay. Let me catch up here. Intervals of increase, decrease. The next item to study is local max or min. Well, you need to use critical numbers. We already saw there are no critical numbers. So we do not have any local maximum or minimum. Okay. So local max minimum, nothing to discuss there. We don't have anything. Look for concavity. So how do we find concavity? Concavity is discussed using second derivative of f. Well, we have already found the first derivative. Let's rewrite it as x plus 5 quantity negative 2. Okay, that's easier to find the derivative of. So second derivative will be 13 here, negative 2 jumps down, decrease the power by negative 1. See, notice this is a chain rule. So I must go in and take its derivative. Well, derivative of this is 1. So I don't get anything more. Simplifying, 13 times negative 2 is negative 26. Power is negative 3. Now bring it back down to make it a positive power. Okay. So the only cut point here is negative 5. You can check. Okay. You can check f double prime x equals 0 cannot happen. Same reason as before. As here, you cannot have a fraction equals 0 when the numerator is not 0. So same story. The fraction cannot be 0 as long as the numerator is not 0. So the only cut point we have here again is x equals negative 5, which is not in our domain. So that is not going to give us an inflection number. So see, neither one. So let's see what happens. Okay. So no inflection point. Okay. Yet we can have different concavities, but this point is not going to give you a point on your curve. So you don't have an inflection point. Let's discuss concavity now. You have two pieces. Take a test point from each piece. Plug in the test points in your second derivative. Aha! When I plug in negative 6, I get negative 6 plus 5, negative number. Power 3 is negative. Numerator is negative. So overall, it's positive. So this is going to be concave up. Here your curve is going to be concave up. To the right of negative 5, well, we chose 0. Plug it in. I get positive 5 power 3 in the bottom, which is a positive. Numerator is negative. It's overall negative. So I'm going to be concave down on this side. Isn't it incredible? You're concave up here, concave down here, but you're increasing both places. All right. So now finally we want to sketch the graph. Okay. So I'll come back to a new video because this might take some time. Okay. See you until then.